Today on AI Paper Slop, we're tearing straight into a paper called xHC, which stands for Expanded Hyperconnections. And the core insight here is that standard transformer architectures, they rely on a single residual stream, which severely bottlenecks how information flows across layers.
Right, it's a huge limitation.
Yeah, and previous work on hyperconnections, or MHC, successfully expanded this to 4 parallel streams. But trying to scale that up to 16 streams just hit this massive wall of exploding compute costs and, well, diminishing returns.
Exactly, it just didn't scale.
Right, so this xHCT paper solves that by introducing 2 key innovations. First is temporal feature augmentation using causal convolutions to enrich the write-back signal. And second is a sparse residual stream architecture that it reads from all 16 streams but only updates 4 at a time.
Which is the really clever part.
It is. And the result is a massive leap in downstream performance on 18 billion and 28 billion parameter mixture of experts models. It basically turns the expansion rate of the residual stream into a viable, cost-effective scaling axis.
Yeah, and for anyone listening who provisions compute for training foundation models, the implications of this new scaling axis are just massive. I mean, we are so used to relying on scaling laws driven by width, depth, and, data.
The classic 3.
Right. But what this paper proves, both mathematically and empirically, is that residual stream expansion is a legitimate orthogonal scaling axis for LLM pre-training. I mean, literally increasing the memory bandwidth of the model's internal representations.
Yeah.
They achieve superior loss curves while demanding significantly less compute than the baseline architectures. It's a big deal.
It's huge. But before we get into exactly how xHC pulls off this magic at 16 streams, or an expansion rate of n equals 16, we really need to diagnose why the previous state-of-the-art MHC choked when they pushed it past 4.
Yeah, the failure mode of MHC at scale is, well, it's purely mathematical. The architecture relies on dense residual mixing. So to generate the residual mapping matrix, the network has to project a massive amount of data. It basically squares the number of streams, so n squared, and then multiplies that by the hidden dimension c.
Right.
So as you scale n, the computational bottleneck scales at the cube of n.
Wait, order of n cubed times c?
Yeah.
I mean, for anyone writing training loops, seeing a cubic scaling curve usually means the architecture is just dead on arrival.
Yeah, completely.
The compute tax would just devour your FLOP budget.
It's a brutal penalty. The researchers actually ran an empirical test on a 2.5 billion parameter MOE model, pushing n from 4 to 16.
And what happened?
The training FLOPs spiked by 32%, but the loss curve barely nudged. I mean, the loss dropped by only 0.006.
Oh, wow.
You're burning a third more compute for essentially a rounding error in performance.
Okay, let's unpack this, because the math punishes you heavily for scaling, obviously. But the paper also mentioned this information supply bottleneck.
Right, which is equally important.
Yeah, so think of it like this. It's like having a team of 16 brilliant researchers. Those are your expanded streams. But you're forcing them all to read from the exact same one-page memo.
That's a great analogy.
Because the network only generates one single write-back signal per layer. So are the extra 12 streams just like sitting there starving for something unique to learn?
They are, yeah. And what's fascinating here is that these 2 bottlenecks, the mathematical one and the information one, they actually compound each other.
How so?
Well, because every layer injects only a single scalar-weighted output into the multi-stream state, the streams cannot physically form distinct, non-redundant histories.
Ah, I see.
They are all drawing from the exact same limited data pool. The network is trying to learn diverse features, but the architecture bottlenecks the supply of information. So yeah, the information bottleneck kills the benefit of a larger n, while the n-cubed projection kills the efficiency. The extra streams just become totally redundant capacity.
So if they are starving for data, where do they steal it from without completely breaking the compute budget? Because you can't just invent information out of nowhere.
Exactly. You have to borrow it from the neighbors. The researchers realized they needed a structurally cheap way to generate richer write-back components.
Right.
And their solution is temporal feature augmentation using multi-scale causal depth-wise 1D convolutions.
Okay, wait. I need a translation on that mechanism. I know causal means we aren't leaking future tokens, which, would ruin autoregressive pre-training.
Right, obviously.
But how does a depth-wise 1D convolution actually enrich the data for these streams?
So think about the sequence of tokens moving through the network. Instead of just looking at the current token state, a 1D convolution slides a window backward over the previous tokens.
Okay.
They use kernel sizes of 4, 8, and 12. So one filter looks at the local context of the last 4 tokens, another pulls from the last 8, and another from 12.
Oh, okay.
This generates 4 distinct components, the original signal, plus 3 new context-aware signals. So your K sub R is now 4.
Ah, so instead of one single memo, the researchers now have 4 different reports summarizing the recent history of the token sequence. That gives the 16 streams enough diverse material to actually start building non-redundant histories.
Exactly. It gives them the raw material they need.
But wait, though, looking at the architecture diagrams, they only apply these convolutions after the MLP layers, the MOE feed-forward layers. Why leave the attention layers out of the fun?
That's a very common question.
I mean, shouldn't we want more historical context everywhere in the block?
It makes sense intuitively, but that instinct often leads to really unstable model design. Consider what attention fundamentally does. Its entire job is to mix information across the sequence dimension.
Right, it's already doing the mixing.
Exactly. It's already highly spatially aware. So if you slap temporal augmentation on top of attention, you are essentially double mixing the sequence. And the authors found that doing so severely destabilizes training.
That makes total sense.
MLP layers, conversely, process tokens in total isolation. They are entirely blind to their neighbors. That makes the MLP sublayer the perfect, clean insertion point for injecting local contextual features without causing any interference.
That distinction clarifies a lot. But, whenever I've tried introducing parallel vectors into a network, I usually run into massive activation spikes.
Oh, yeah.
If these convolutions are pulling from overlapping token windows like 4, 8, and 12, aren't their outputs going to be highly correlated with the original layer output?
They absolutely will be, and that is a massive stability risk.
Yeah.
If you naively dump highly correlated parallel vectors into the write-back signal, they artificially amplify the signal in one specific direction.
And then your activations just grow exponentially.
Right, and your gradients explode. So to solve this, xHC applies Gram-Schmidt orthogonalization directly to those convolutional components.
Oh, nice. Basically stripping out the redundant parallel parts of the vectors so every single component is genuinely pointing in a new, distinct mathematical direction.
Exactly. It ensures the network only absorbs the strictly novel information from the temporal context. This keeps the write-back components mathematically distinct, which, keeps the training completely stable.
Okay, so we've solved the information starvation. The 16 streams now have rich orthogonal data. But we are still staring down the barrel of that cubic compute penalty if we try to update all 16 streams at once.
Yeah, the math doesn't just go away.
Right.
Yeah.
So the paper solves this by splitting the read and write operations through structural sparsity. They read densely, like every layer accesses all 16 streams, but they write sparsely, only updating 4 active streams at a time.
Yes.
Here's where it gets really interesting. It's like a corporate board structure where all 16 executives are required to read the master brief. That's the dense read. But only a 4-person committee is actually authorized to edit the master document, which is the sparse write.
That's spot on. And the sparse write is what completely saves the FLOP budget. By only updating 4 active streams at any given layer, so K equals 4, the dominant residual mapping generation cost drops from the cube of 16 down to the cube of 4. So you maintain the massive memory capacity of 16 streams, but you only pay the compute tax of updating 4.
Which is incredible. But I'm assuming that dense read is totally non-negotiable.
Oh, absolutely.
Like if we didn't force the network to read all 16 streams at every layer, and a stream gets updated at layer 10, it might just get completely ignored at layer 11. The whole cross-layer information flow would just snap.
You would introduce catastrophic information disconnection. By enforcing that every single sublayer reads from the full 16 stream state, the network ensures that any information stored anywhere in the residual memory remains globally visible.
Even if it's not being updated.
Exactly. The network can access that data regardless of which specific streams are currently selected for writing. What's really crucial here is the synergy. Neither of these fixes works alone.
How do you mean?
Well, without sparse writing, the compute costs remain cubic and unscalable. But without the temporal augmentation we discussed earlier, the sparse updates are just efficiently shuffling around redundant, useless information.
Oh, yeah.
By combining them, they drop the FLOP's overhead to just like 3 to 4% over a standard vanilla transformer baseline.
That is wild. But wait, how does the network actually choose the 4-person editing committee? It can't just be a standard top K routing, right?
Yeah.
Because those mechanisms are notoriously unstable during early training. You always end up with dead routing paths.
Yeah, routing collapse is a huge issue. The authors avoid that with a fixed plus routed scheme.
Okay, how does that work?
So 2 of the active streams are fixed. They are always active no matter what.
Oh, I see.
This guarantees a persistent, unbroken gradient path flowing backward through the entire network. Then the other 2 streams are selected dynamically via a top K routing mechanism based on learned importance scores.
Let me guess. If they're calculating importance scores across 16 streams, they aren't using a softmax activation. I mean, softmax usually creates a winner-take-all dynamic where 1 or 2 options just dominate and the rest die off.
That is the exact failure mode of softmax in routing. So yeah, they use a sigmoid activation instead.
Makes sense.
Softmax forces all the probabilities to sum to 1, which creates a highly competitive environment where streams just cannibalize each other's scores. Sigmoid, on the other hand, evaluates the importance of each stream completely independently.
So they aren't fighting for a slice of the same pie.
Exactly. This keeps the utilization across all 16 streams much more balanced.
Okay, so the theory is elegant. I'll give them that. But for the ML engineers listening who actually have to deploy this, the only metric that matters is whether it scales on massive MOE models.
Okay.
Like, what do the actual downstream numbers look like?
The empirical proof is incredibly strong. On an 18 billion parameter MOE model, xHC boosted the average downstream score across all benchmarks from 44.8 on the MHC baseline up to 48.8.
A 4-point jump is massive at that scale.
It really is. And when they pushed the architecture to a 28 billion parameter MOE model, it added a solid 3.1 points over the baseline. We are seeing systematic, across-the-board improvements in reasoning, coding, mathematics, and, general language understanding.
And tracing the scaling laws, the efficiency gains are just ridiculous. Like, to hit the exact same loss target, a vanilla transformer requires 1.5 times more compute than xHC.
Yep.
Even the previous 4-stream MHC model requires 1.19 times more compute. If you are running a multi-million-dollar training cluster, shaving 20 to 30% off your compute budget for the identical loss target is, that's a career-making optimization.
Oh, absolutely. The budget implications are massive. But, we need to look closely at the optimizer setup because this is where novel architectures frequently break down.
Right. When you move away from standard AtomW, things tend to get a bit fragile.
Exactly.
Yeah.
And the researchers tested xHC heavily with the muon optimizer, which is gaining massive traction right now for the backbone parameters.
Okay, so what does this all mean for the optimizer? Are we just applying mu to everything? Because I need some help untangling this part.
It's a bit nuanced.
Because muon uses Newton-Schultz iteration to construct orthogonalized matrix updates for the network's parameters, right?
Yes, it does.
But earlier you explained that they were using Gram-Schmidt orthogonalization on the temporal features to keep the math stable.
Yeah.
If the optimizer is doing matrix orthogonalization and the architecture is also doing vector orthogonalization, do those mechanics clash?
It is a brilliant catch, and the authors realized the exact same conflict. They actually dropped the Gram-Schmidt step entirely when using the muon optimizer.
Really?
Yeah. Muon's Newton-Schultz iteration physically controls the spectrum of the update matrices. It basically forces the weight updates to maintain healthy orthogonal directions naturally.
Oh, so the optimizer just handles it.
Exactly. Because the optimizer handles the stability, the network becomes highly resilient to those correlated inputs from the convolutions. Doing Gram-Schmidt on top of muon actually restricts the gradients too much and degrades performance.
So does that mean we just apply muon blindly to every single parameter in the xHC architecture and call it a day?
Not quite. There is a very specific limitation with muon. Newton-Schultz iteration does not behave well when the input dimension of a matrix is massively larger than its output dimension.
Yeah.
It really struggles mathematically with highly unbalanced projections.
And in the xHC architecture, the network has to project from a massive hidden state NC down to just a handful of routing weights, N, to pick those 4 active streams.
Exactly. That unbalanced projection is the friction point. So they use a hybrid approach. The heavy lifting, the attention, and MOE projections are trained with muon. But the stream control projections, the ones managing the sparse routing, they stay on AtomW.
That makes total sense.
And the fact that xHC still delivers massive gains under this hybrid setup proves that its architectural efficiency isn't just a fragile illusion created by tweaking the AtomW optimizer. It genuinely routes information better.
Okay, we have to talk about hardware realities now, because this is where the rubber really meets the road.
Yeah.
FLOPs might be relatively cheap on modern GPUs, but memory bandwidth is the real currency. It is the absolute bottleneck.
Always.
We established the FLOP overhead is only like 3 to 4%. But if you have 16 full streams in memory and you are forcing a dense read of all 16 at every single sublayer, I mean, you are going to create a catastrophic I/O traffic jam on your H100 clusters.
The memory bandwidth math is definitely sobering.
Mhm.
A standard xHC setup requires 73.5 times the hidden dimension in memory traffic per sublayer.
That's huge.
Just to give you context on how heavy that is, the older 4-stream MHC model only required 34 times the hidden dimension.
Yeah.
You are more than doubling the volume of data you have to shove through the GPU's memory bus.
Yeah, if you try to deploy that naively, your training throughput will just crawl, regardless of how few FLOPs the GPU is actually executing. Because at every single sublayer, the hardware has to perform 2 massive reads from high bandwidth memory. First, 1 full read of all 16 streams just to figure out the routing scores, and then a second full read to actually aggregate the dense output state.
It's incredibly inefficient on a hardware level.
So to prevent this, the paper introduces a mechanism called xHC-Flash. How does it manage to get that memory traffic back down?
So xHC-Flash operates on a principle of operation amortization. Instead of computing the routing decisions from scratch at every single sublayer, it calculates a single routing decision at the very beginning of a transformer block.
Okay.
It then shares that exact same routing decision across both the attention sublayer and the MLP sublayer. Furthermore, it jointly pre-computes the dense mapping weights for both sublayers at the start of the block.
Wait, hang on. If I pre-compute the dense read mapping at the very start of the block, how do I account for the fact that the attention layer is going to fundamentally alter the state of the active streams before the MLP layer even gets its turn to read them?
That's the trick.
Because wouldn't the MLP layer just be reading totally stale data?
This is arguably the most elegant engineering trick in the entire paper. They completely rip out the residual mixing on the attention side.
Really?
Yeah, they defer all the active stream mixing entirely to the MLP side. Because the attention layer is now restricted to just applying a simple scaled addition to the active streams rather than a complex mix, the MLP layer can use a technique called exact dense read reuse.
Let me see if I am tracking the math here. Because attention only performed a simple addition, the MLP layer just takes that pre-computed baseline read from the start of the block and then applies a tiny, lightweight scalar correction based on whatever the attention layer added.
That is the exact mechanism, yes. It mathematically reconstructs the perfect updated state it needs, but it entirely bypasses the need to trigger a second massive read of the full 16-stream state from the main memory.
That is absolute genius. You get the mathematical equivalent of reading all 16 streams without actually paying the heavy I/O cost to read them twice.
Exactly, and the paper pushes this even further with a 4-sublayer variant. By sharing his routing and readout process across 2 full transformer blocks, so 4 sublayers, in total xHC-Flash 4-sub brings the memory traffic all the way down to 40 times the hidden dimension.
Which brings it remarkably close to the 34C traffic of the old 4-stream baseline. But you get all the massive representational and reasoning advantages of maintaining 16 distinct streams.
Yep. And if we connect this to the bigger picture to truly make this architecture sing on NVIDIA hardware, they went a step further and wrote custom Triton kernels.
Oh, of course they did.
Yeah, kernel fusion plays a huge role here. By fusing the dense pre-mapping read and the sparse residual mixing into a single Triton kernel, they physically prevent the GPU from constantly writing intermediate states back to the main memory. You perform all the math in the ultra-fast RAM and only write back when the block is finished. It avoids launch overheads and massive bottlenecking.
That kind of full-stack engineering, taking a theoretical math concept like causal convolutions, solving the memory bandwidth bottleneck with amortized routing, and writing the bare metal Triton kernels to fuse it all together, that is what elevates this from a neat math trick on our cuff to a production-ready foundation model architecture.
It really is the complete package.
So let's bring this home. The researchers successfully unlocked residual-stream expansion beyond the traditional breaking point of 4. They managed the information supply with temporal augmentation, and they crushed the compute cost with structural sparsity, resulting in a highly efficient, deployable architecture.
Exactly. And the sheer success of xHC leaves us with a genuinely profound question for the entire field of deep learning.
Yeah.
We now have concrete mathematical and empirical proof that the expansion rate n, the number of residual streams, is a highly efficient, cost-effective scaling axis, behaving just like layer width or network depth. So what happens to model architecture when that number scales to 64 or 128?
Wow. Yeah, that fundamentally breaks how we think about the shape of transformers.
Right. Could we eventually see architectures where the traditional depth of the network is drastically reduced? I mean, imagine a model that doesn't need 80 or 100 vertical layers anymore, because the vast majority of its capacity, its historical context, and reasoning power is stored purely in a massively parallel, hyper-expanded horizontal residual memory.
If a model can process a complex coding problem and pull nuanced context from 128 parallel streams of historical memory at, a fraction of today's compute cost, the entire paradigm of how we design foundation models might just flip on its side.
It's a very real possibility now.
That is a wild thought to sit with the next time you are provisioning your cluster budget. Thanks for tuning in to AI Paperslop, and we'll see you next time.